All right. So, first off, let me apologize for not explaining the marking schedule very well to you guys, because you guys are very clearly stressed out about part A, and I want you to know that it's not that bad, okay? And I know you guys heard me say, wait, we're not done with this assessment? No, we are not. This is part 1 of 4. It's a 4-credit internal. The good news is you can think of each section as 1 point, but not really because you got to get all of it. All right. So I just want to show you guys the requirements for achieved merit and excellence for part A, because remember, you do have to pass the multiple components of this assessment to pass. The good news is they have built in places for you to make mistakes, so it's not like an all or nothing kind of thing, okay? So for part A, and most of you guys, I could see you could do this, is you develop a workable plan, carrying out trials, realizing a dilution is required, and doing some sort of dilution factor. If you're at the achieve level, you've given me a bad dilution factor and your stuff doesn't make sense. All right, the good news is, looking at everybody's work, I don't think anyone's there. All right, most of you guys know what you're doing with these calculations, so that's the first thing to tick off, okay? Phew. All right, for the merit, what I was looking for was if you developed a workable plan. So the dilution factor that you did and the titrate volume makes sense. So between 8 and 30. Again, most of you guys, hey, going over the marking schedule, you might want to know this. Most of you guys were fine with this. Again, I checked your calculations, and a lot of you guys knew how to do the calculations. So if you could do the calculations, you're on track for at least a merit, okay? The other thing is that I need you to explain how you do the dilution, and I'm going to look at that in 2 places. I can look at it in that scaffolded paragraph, and I can look at it with the prep work you were doing to make those plans. All right? So most of you guys can do that. Most of you guys are going to probably be at the merit for this part A. All right, the excellence component was that justification on the back and explaining why you need to dilute and how your method is valid and accurate. All right, if you mucked up the justification, the good news is you can still get excellence because you can talk about it in part D, actually. So I will give you a method in part C. You'll be able to compare and contrast the method I give you in part C, the one you created, and you can explain once again what was wrong with your original method. So you get a backup to still get the excellence if you don't get the excellence on the first go. But I expect most of you guys will probably be fine. Okay? Are we okay with that so far? Yes. Does that has that alleviate some of the anxiety?
No.
A little bit? Okay. No? All right. Are we okay with that so far? And that's my fault. I should have probably communicated that better, and I should have printed this out for you guys to see it. Forgive me? Okay. Shall I talk about the next part?
Yes.
Okay. So let me show you what part B is. And in fact, part B and part C are very, very similar. So, part B and part C. All right, doing the new parts now. Probably should be listening. All right, part B and part C. Can we not like take more masks than we need because I actually pay for those out of my own money? Okay. Just I saw a lot of people grabbing masks. Okay. I'm happy for you to grab another one, but it's just like don't like I see people like double masking and then drawing on their mask and just obviously not like using them. Yeah. All right. Can I talk about part B and part C?
Yes, you may.
Okay. Part B and C are very similar when it comes to their calculations. So part B and C doesn't really have a lot of writing, but it does have math calculations that you need to do. They are slightly different because you're going to do them in a different order, but the process is more or less the same. Yes?
Are we allowed to use a calculator?
Yes. Always. All right. I want to show you guys the marking schedule so you can see how it's built in. The difference between part B and part C is that part B, I give you the data. Part C, you are doing the titration and collecting the data yourself. That's the main difference. So there's stuff you need to do for the achieved for Part B and Part C. But the good news is for the achieved, there's lots of different ways that you can show me enough evidence for achieved. You see how there's all these or options? It means that I just need to see that you can do like one section of Part B. So you can make a mistake and you'll be okay. All right? Part C is not focused on the titrations, it's focused on the practical. We okay so far? All right. So then when we're looking at the merit requirements, obviously Part C, again, there's going to be a component that is the titration and the practical, that's part of your grade. But the good news is that the calculations that you're doing in Part B and Part C, you get 2 chances at if you're trying to get a merit. So I need to see that you can do the calculation correctly once. Either you do it correctly in Part B with the data that I give you, or you do it correctly with your data in Part C. So you see, again, there's an or option here. All right? So if you make a mistake, but you got it on the other one, you're fine, you can still get a merit. For the excellence, you need to get both Part B and Part C when it comes to the calculations. You see how the calculations is now an and instead of an or. All right? Are we good so far? So that's what Part B looks like, and then Part D is just your write-up. I don't want to go through it because I don't want you guys to be overwhelmed. So what I'm going to do today is I'm going to start teaching you guys the Part B things, and the good news is that with the Part B stuff, we can double dip because the calculations, like I said, are very similar for Part C. It's just going in a different order. Are we good? All right, keep going?
Yes.
All right, or do you guys need a break? What time does this period end? 25. Do you guys want to get a quick break?
Yes.
All right, take a quick break. Come back in like 2 minutes. Okay, so in order to do Part B, there's obviously, like I said, calculations. But I don't want to dive straight into Part B without giving you guys some like preamble first so you can understand what you're doing and why you're doing it. So the first thing we got to keep in mind are some units. So you guys, I'm just going to switch over to the document camera. You guys would have seen things like grams. You've also would have seen things like moles as various units, correct? And you might be wondering, what does that even mean? You also might have seen things that were grams per liter. You might also see it being written G to the -1. You might also see things being written as moles per liter. You would have seen this in bio. Again, moles per liter you could write as -1. The shorthand of writing that is the big M for molarity. You might have seen this in bio because if you guys remember when you were doing your turnips, you were putting them into different salt concentrations and you saw stuff that was like 0.1 mole, 0.3 molar, 0.5 molar. Does this like ring a bell? Some of the stuff you saw in biology. And so basically what I'm trying to do is talk about this unit here and where we got that unit from. So mole is a new type of unit that we are talking about. You guys have seen grams before, and grams is referring to weight, correct?
Yes.
So like grams of chicken that you buy at the supermarket, things like that. Or kilograms of like when you go to the doctor and weigh yourself. So this here is a measurement of weight. Basically, when we're talking about weight, we're talking about mass times gravity. Mole, however, is a little bit more useful for us in chemistry because that one talks about amount. Are you okay with that so far?
Yes.
So, if I was, for example, going to compare things on the periodic table and I wanted to compare 2 things together, let me show you what I mean. So let's say, for example, I wanted to compare hydrogen versus helium. Are we okay with that so far? Now, when I look at the atomic number for hydrogen, the atomic number for hydrogen is 1. or sorry, the atomic mass, I should say, is 1, and the atomic mass for helium is 4. So I'm just going to write down 1 and 4. So that is both referring to atomic mass. Are you okay with that so far? We good? Do you guys remember what atomic mass is referring to?
The amount of
Protons and neutrons in the nucleus. So basically how big that atom is. Yeah.
so almost like atomic mass.
It's related in there. So if I was, for example, comparing 5 grams of hydrogen to 5 grams of helium, they are the same weight, but these guys are different size atoms. So when it comes to the quantity of atoms, would this number be the same?
Wait, what? Yes. No.
No. So do you see how this is a bigger atom than this one here? So if I had 5 grams of helium and 5 grams of hydrogen and 5 grams of helium, I wouldn't have the same amount. I would have the same weight, but not the amount of atoms. Are you okay with that so far?
Yes.
Which one would have more atoms, do you think?
Helium, right?
The hydrogen, because it weighs less. So this would have more atoms. Because they're smaller. So more atoms of, if I was doing 5 grams of each, this one would have more atoms. Because it's smaller. Yeah? Huh? Do you need me to backtrack? All right, can I keep going? Are you okay with that so far?
Yes.
All right. Like I said, mole is referring to quantity, so it's referring to number of atoms. So if I have 1 mole of hydrogen and 1 mole of helium, would I have the same number of atoms in both cases?
Yes.
Yes. So in this case, we would have the same number of atoms. So which one do you think is a more useful unit for chemistry?
Mole.
The moles. If we think about chemical equations, you know how in chemical equations that you have those numbers in front and things have a ratio to each other? That's referring to the moles and things like that. Because obviously when I think about the chemical equation, I need to have a certain amount of this reactant and that reactant to have the reaction occur. So that's why you want to use moles. We create this number of moles because it's a unit, and this unit is just referring to a specific number of atoms. So the mole unit is equal to 6.02 times 10 to the 23 like particles or atoms. Or molecules, whichever you want to refer to that. So it's a really, really big number. Now, you don't have to worry about ever converting it to particles or to atoms, but I'm just saying that's where you pulled that number from. So in both of these cases, I would have 6.02 times 10 to the 23 atoms in that 1 mole. So this is quantity comparison. Are we okay with that so far?
Yes.
All right. So if we're looking at this periodic table, these numbers here for the atomic mass is referring to grams per mole. So what that means is if I, for example, weigh out I'm just trying to get a different color. If, for example, I weigh out 1 gram of hydrogen and I weighed out 4 grams of helium, these two would have the same number of atoms because now I'm using their atomic masses. Are we okay? Should I do some more calculations to show you what I mean? So this is the mass that would have the same number of moles. Cool. And let me show you guys some calculations so you guys can see how it all fits together. So basically, I want to be able to convert from grams to moles. The problem is I can't measure things out in moles when I'm in the lab because then I have to go through and count particles. So what I use indirectly is the weight. So if I know how to do that conversion, then I know what to weigh out on the scale, and then I know the number of moles based off the weight of what I have. So let me show you guys some calculations so you guys can see how we do that conversion. Because like I said, I'm not going to sit there counting atoms. Okay? I know. Don't want to sit there counting atoms. All right, can I move it?
Yeah.
All right, so let me show you guys how to do this. If anybody needs the paper, feel free to grab the paper from my desk. All right, let me see what examples I had in my board. Oh, I did not write any examples. Okay. Cool. That is okay. I will actually maybe do the first part of a lot of these questions. Let me give you guys some example questions, but we'll just do the first step, okay? So let me show you how you might come across these numbers. All right, let me show you how some of this works. All right, so I just want to do the first part of a lot of these calculations. We can finish these calculations another day, but I just want to show you guys like how to start setting up. So, like I was saying, for a lot of these things, I want to have my units in moles, but the problem is that a lot of things are going to be in grams because that's how I weigh things out. So, let me give you guys an equation. So, and you're going to hate this equation because the letters are stupid. I don't know why they selected these letters, but they did. All right. So, the moles, which is N, is equal to the mass divided by the molecular mass, which is your big M. All right. I'll write it down. Sorry, that's a big M. All right. Little n is the moles.
What is the big M?
I'm giving you the formula first and then I'll do the calculations. These, I know, it's a terrible equation because it's M's and N's. All right, the little m is mass, and the unit for that is in grams. Yeah? Write it on your book because then I'll do the calculations on the paper. I just need to give you the formula first. And the big M is referring to molecular mass. So that's grams per mole. Per mole. So this molecular mass is coming off the periodic table. All right, can I keep going? Ready for me to keep going?
Yes.
Okay.
Yes.
All right, so I just want to do the first part to both of these example questions. We'll worry about concentration later. All right, so this first question here is asking, what is the concentration if I took 2 grams of sodium carbonate and added it to 0.1 liters of water? So whenever you see them give us a concentration, they're going to want the answer in moles per liter. But the problem is they have given me grams. You see how this is in grams? So I need to convert the grams to moles. That's what I'm going to show you.
With the weight, it's like a.
With the weight. All right. The first thing I need to figure out is the molecular mass of this compound. So how do we figure out molecular mass? Look at the periodic table. So I see that I have sodium, and sodium has an atomic mass of 23. So I'm doing 23 times 2, because I have 2 here. I'm going to add in my carbon. What's carbon's atomic mass? That's the atomic number. Atomic mass is 12. I want the weight of it. And then the last thing I have is oxygen, which has the atomic mass of 16. 23 came from the atomic mass of sodium. And I have 2 of them in that formula. All right, so I have 16 times 3. So let's plug that into the calculator. 23 times 2 plus 12 plus 16 times 3. My molecular mass is 106. Grams per mole, because we're talking about molecular mass. Oxygen's right here. Yeah? There's oxygen in the molecule, and I times it by 3, because it's 3 oxygens. So that's how I got this one. All right, keep going. All right, now that I have this information, I can start plugging it into that N equals M divided by big M. So N is equal to the mass. The mass is 2 grams. And I'm dividing it by 106 grams per mole. And I like to write the units down because then I can double check that I have set up my equation correctly. So the grams should cancel with grams because I'm doing gram divided by gram. And since I'm doing per mole, it becomes just mole. So 2 divided by 106, I get this teeny tiny number, and that's going to be quite normal. 0.018. I'm going to leave it unrounded because we should round at the very end. I'll just stop it at there because I'm running out of space.
7?
Yeah, I'm going to round it to 7. All right. Are we okay with that so far? Yeah, not too bad? All right. Cool. All right, shall I give you guys another example working in the other direction?
Yes.
All right. Unfortunately, on my piece of paper, I don't have an example of one of those, but we can make up a question. So let's say, and we can keep using this example here, and I'll just change my color to a different shade of blue, if I have another shade of blue. Let's say I have, trying to think of a number I would like. Let's say I have 15 moles of the sodium carbonate. What is the mass of it? So this is now going back into my notes, because I know some of you guys are thinking about what's on the sheet and what's going on my paper. So, for example, if I was trying to work backwards, I have the moles, and I want to figure out the mass. So you see how you have this original equation? I'm going to rearrange it to solve for mass. So if I was to rearrange it to solve for mass, I would have mass is equal to the moles times the molecular mass. I just rearranged the equation to solve for mass. Do you want me to show you how I did that? All right, so what I did was I want to get the little m by itself. So I multiplied both sides by the big M. The big M then cancels out. So now I have mass equals the moles times the molecular mass. That's how I move the equation around. The other option is you can just plug in the numbers and move it based on the numbers. So you could go 15 equals m divided by the molecular mass we had solved earlier, which is 106. So you can work that way too. And then just multiply by 106. Because then that cancels out. Yeah, because whatever you do to one side of the equation, you need to do the other side of the equation. It's algebra. I'm sorry, it's coming back. All right, so mass is going to be equal to the moles. So I have 15 moles times the molecular mass, which we solved earlier, 106 grams per mole. The moles cancel out, so I just have grams. So I would do 15 times 106. So I would need to weigh out, if I wanted to get 15 moles, 1,590 grams. That's what I would weigh out on a scale to get 15 moles of sodium carbonate. That's how much I would weigh on a scale. Because I can't go through and count atoms. Because if I was trying to count out 15 moles of atoms, it would be 6.02 times 10 to the 23 times 15. That's how many atoms or how many ionic compounds of sodium hydroxide, or sorry, sodium carbonate I would need to count out. 1, 2. I'm not going to do that. I'm going to do this conversion, and I figure out, okay, what is the mass of 15 moles? And then I can put that on the scale. So that's how we're doing these conversions. I know. We'll stop it here. Okay? So what I need you guys to do for practice then is in the internal SciPad, there are 2 pages to practice the calculations. It is page, I think I'll have it on the Google Classroom. Page 8 and 9 on your SciPads is what I want you to do to follow up these calculations. Okay? Huh? Page 8 and 9 is your homework. 8 and 9. It practices the mole concept, and it also practices that conversion concept. I'm going to do 8 and 9 because I'm going to keep going in our next lesson. I'm sorry that I have to give you math. It's just algebra, though. I know you don't like algebra, but it's basic algebra, okay? I know. But this is just real big. Like, you just gotta move things around. Okay? I'll scan all these notes. I have this recorded. We'll finish the story next week.